So the last one of 2023, we've often had as the lecture, we usually have an astronomy lecture actually at the end of the year, and we would always have Dr. Jim Kaler come and give those talks. But we are pleased to be having Dr. Kirk Barrow, Professor Kirk Barrow from the University of Illinois Department of Astronomy, now here to give us this talk, which you can see up on the screen there. It's The First Light, Unraveling the Origins of Stars and Galaxies and Black Holes in the Early Universe. Before joining the University of Illinois, Dr. Barrow earned his bachelor's, master's, and PhD over at the Georgia Institute of Technology. I guess you usually call it Georgia Tech if you're seeing it on Saturdays, right? And then after that, he had performed postdoctoral research over at the Harvard and Smithsonian Center for Astrophysics. I don't think I gave that the right order for the current naming for that organization, but nevertheless, he also worked at the Kavli Institute at Stanford University, and he was also at the Kavli Institute at the University of Tokyo before he came here to Illinois. Anyways, I hope you folks have lots of great questions for Dr. Barrow. If you do, feel free to raise your hand. Are you okay with them asking questions during the talk, sir?
I love questions.
Excellent. Okay. Well, I'll make sure that they stay on mic. So if you do have a question, make sure to call me over, and I'll be happy to make sure that your voice is heard. All right. Well, folks, I'm going to head back there to help move us through the slides, and I'm also actually going to turn off our snowflakes too. So I hope you all enjoy this talk. All right. Thank you, Dr. Barrow, for joining us.
So I'm going to have to signal to Eric in the back when I want to change slides. So it's going to be a little awkward, but we're going to get through it. All right, so let's begin. Great. So science is a very collaborative process, and as a professor, I'm always tasked with mentoring the next generation of researchers, and that means that I want to start all of my presentations, no matter what the topic is, as long as it's related to my research, with my team. So this is an outdated picture from spring of this year. So that was after my first year. We took this picture at the UIUC Observatory. And this was my team at the time. Could you go forward a little bit?
Trying to turn down the gain, sorry about that.
No, you're okay. So these are my research members, and they look at topics from black holes to stars to merging galaxies and all these other topics. Could you go forward? And I'm also mentoring Lillian at Stanford, who's doing research in machine learning. So this is just my research group, and I wanted to make sure that they get credit where credit is due. All right, so let's begin the actual talk. All right, so I wanted to begin with just explaining and sort of walking you through the first 1 billion or 5 billion or so years of the universe. So it'll be a short walk through that time. All right, so let's start at the very beginning. So you've all heard of the Big Bang. So the Big Bang is an event that happened 13.8 or 13.75 billion years ago. The timing is actually not perfectly known. And we assume a Big Bang because we know the universe is expanding, and if you turn that backwards, everything goes down to nothing, right? So we assume that 13.75 billion years ago, there was a Big Bang, and the universe started expanding from that point. Now, there's a problem with that. You have a question?
So is the first millisecond or nanosecond covered by quantum mechanics or relativity, theory-wise?
So, well, if you're talking about Planck time, that's a time when all of the forces that we know of were sort of unified. There's a theory of of the unification of those forces, and we don't have a quantum theory of gravity. General relativity will explain how the universe expanded, so there's a little bit of general relativity at that point, but we don't have a unified theory at that time. And I'll actually talk about why we don't have a theory that exactly explains the Big Bang in that very first nanosecond or earlier point in time. So, but I will say that if you look at how fast the universe is expanding, and you draw back in time, could you go to the next point? There's actually a little bit of a problem. The universe looks the same in every direction. So if the universe looks the same in every direction, if you look at one side of the universe, it looks a lot like the other side of the universe, then there's a little bit of an issue, because that means that those two sides of the universe must have been connected at some point. You don't randomly get two things to look the same. And the only way that they could have been connected is for the universe to have been much smaller than our current expansion suggests. And this implies that there was a time in the early universe where the universe expanded extremely fast. It grew 10 to the 50 times as large as it was in a very, very short period of time. So 10 to the minus 35. So this is ridiculously small amounts of time the universe expanded very quickly. This is called inflation. So this is how the universe began. All right, next slide. The second thing that happened for the first few million years is what we call Big Bang nucleosynthesis, the creation of all the elements and things in the universe. So as the universe started to expand, it started off very hot. It was a big bang, and then it started to expand. And when it expanded, it started to cool off. And you got the first protons and electrons and neutrons, the things that make atoms. They started to freeze out of the universe. So the first three elements that were formed in the universe were hydrogen, helium, and lithium. Just a tiny, tiny bit of lithium, but mostly hydrogen and helium. And this is some chemical equations, but basically, in the early universe, you could turn any one of these particles back and forth, but as the universe cooled, you could only go one way, and you were just left with a certain number of protons and neutrons. So this is the magic ratio. So atoms are made out of protons and neutrons, and there are 7 protons for every neutron in the universe. All right. So that happened in the first few seconds. After 376,000 years, the universe continued to cool, and it finally reached a time we call recombination. So when things are very hot, electrons and protons, the particles that make up atoms, they can't stick together because they're too hot. So after a period of time, the universe cools enough that they can stick together, and they finally come together. So this is where you actually get the first atoms forming. So this is a little bit of a diagram, and this has a consequence. So before the atoms form, there's a big soup of energy where matter and light are all connected together. But when the atoms form, light is finally able to escape, and it flies off from the primordial soup. So if you go to the next part. And we can actually see the light, the very first light of the universe. When the first atoms were made, all the light was released all at once, and we can look up in the sky at a very specific wavelength, and we can see the light from the very early universe, so only a couple 100,000 years after the Big Bang. And this light is called the cosmic microwave background. Now, this is a famous result that we discovered in the 1960s. It was thought to be just noise or an error in the sky, but if you look anywhere up in the sky and in the microwave frequencies, you can see light. And this is light we sort of call the echo of the Big Bang. Now, referring to the question I got earlier, the consequence of this is the first light that we can see in the universe. Anything earlier than that, we can't see. So that whole time, inflation, the creation of atoms, all of that stuff, we cannot see. And we can't see because the light is trapped until this point in time. And that means that everything before that time is a theory. And we have evidence, we have things that sort of point to the way things were, but we can't see it. We cannot use a telescope and try to see that period in time. Okay, so let's talk about what I do. I run what we call cosmological simulations. So what these are simulations of the entire universe. Cosmological meaning the cosmos, the growth and building of structure and of the universe and galaxies and these things. But in order to simulate the universe, you need a lot of ingredients. So I have a recipe for these simulations. So that light from the early universe, that one bright thing that you can see all across the sky has information in it about where everything was at that time. And this is wonderful for a physicist because it means you know how things started. So if you know how things evolve and you have where things started, that means that you can, from that starting point, figure out everything from there on if you're really good at it and you really know everything. We don't know everything, but we like to pretend we do. So we start with a box. We literally simulate the universe as a cube. And we take information from the cosmic microwave background, and we see that there's slight deviations and perturbations in the matter at that time, and we just propagate it forward. Then we apply gravity and hydrodynamics. Hydrodynamics is how gas and matter interacts with itself. So we have gravity and hydrodynamics, and then we apply the fact that the universe is expanding. So that's a mathematical equation that we apply to our simulations. And we do this in reverse. It's kind of funny. We actually shrink the universe in our simulations, and it turns out to be mathematically the same thing. And what we're missing, of course, are stars, right? Stars are wonderful, complex things that we can't just, that need to come out of our simulations sometimes. So we don't actually simulate the formation of a star. We know when stars form, and then we just put it in our simulations. And then the last element is that we take the radiation, so the light from the stars, and the light from the stars has an effect of warming the universe and affecting chemistry and doing all of these things. It heats our planet, gives us energy and all these things. So we need to have the radiation from the stars. So every single star needs to have light coming from it and simulated in these simulations. And then the final fun thing is we have black holes and certain things like that when we have the right conditions for them. So these are this is the recipe I use to create a simulation of the universe. Okay, so here I have an example of that simulation. One more click might play it. Okay, so the left is a density plot, center is a temperature plot, and then the right is metallicity. And metallicity is where you go from hydrogen and helium to heavier metals like carbon and oxygen, and you can see where they're forming. And if you looked at it very carefully at the beginning, it was kind of just a fuzzy mess, but now it looks a little like a web. And this is an interesting consequence of gravity and the expansion of the universe, is that when you let things go, when you use physics and go forward, so this is the beginning, how it looked at the beginning, everything collapses into something that looks a lot like a spider web. And galaxies form where the spindles of the web meet each other. So if we could see all of the things in the universe, it would look like a web, but we only see the stars, so we only see them as points in space. Okay. All right, so let's move forward. We've only gotten through a couple million years, and we have billions to go. So how does this happen? We start with the CMB. We only have very small fluctuations, and then we know that if you have a little bit of the universe that's more dense than another part, then it'll attract more matter through gravity, and it'll start collapsing. And as the universe is expanding, it's continuing to cool. So we're talking about a universe that's now quite cold. It gets colder and colder and colder as it expands and cools. So this era of the universe is called the Dark Age. And it's called a Dark Age because there's no stars. This is an era before there are ever any stars in the universe. 150 million years of nothing, no light at all. The universe that's just getting colder and colder and colder. And I'd love to tell you all I can about this era of the universe, but we don't have any light from this time, so there's nothing I can show you. It's not a pretty picture to show you. But as time goes on, the universe collapses into into the cosmic web, as you can see here, and eventually some regions get dense enough that it actually falls and collapses into stars. And stars are very dense objects, so it takes a long time for gravity to pull everything together into a star. All right, so this is a So usually when I give a talk like this, I talk about what happens when you have a cloud of interstellar gas and you get 3 different results. So if you could show the 3 results, keep going. So there's 3 things that can happen. If you collapse the gas cloud under gravity, you can either form, 1, a black hole. So everything falls into one place and then becomes so dense that it collapses into a singularity under its own gravity and turns into a black hole. Or it can turn into case B, it can turn into massive stars. Or it can turn into case C, it can turn into stars that are around a lot like our sun. And these 3 things are all possible. And the only difference between them is what the gas cloud is made out of. So early universe, the gas clouds were just made out of hydrogen and helium. So they were more likely to do case A and B. And the late universe, kind of like today, the gas clouds are full of elements like carbon and oxygen, and they cause things to collapse into smaller things, and we get something a lot like stars like our sun. So this is what sort of determines it. It's just chemistry that determines how these things collapse. And that means that I need to have chemistry, actual chemistry inside these simulations as well. So you have to have atoms reacting in these simulations, as well as galaxies forming. So this is crazy differences in scale. So this is one of the difficulties of these simulations. Okay? So after 150 million years of the dark ages, the first stars form. And the first stars, they begin to heat up the universe again. This era is called reionization, and it's called reionization because reionization is a process where we break apart an atom into a positive and negative charge, and this happens if you're hot enough. So the stars will break up all the atoms in what we call the intergalactic medium, and it'll go from being cold to being very hot. So we call this era reionization. It lasts for about 1 billion years. And we have evidence of this. We have observations of this because now we have light and we can see how it's affecting things. So this on the left is the EDGES result, which was famous for a couple years ago for seeing the light that actually sort of signified the beginning of star formation. And on the right, we have something called the Lyman alpha force. And it shows how things are absorbing light as light moves through space. All right. Now that brings us to the James Webb Space Telescope. So this is a telescope that launched Christmas 2 years ago from Karu in South America. And this is something that we've been working on for a ridiculous amount of time. And it's been delayed a ridiculous amount of time. And I wrote my whole PhD thesis on it, expecting it to be done in 2018, but it didn't happen. But it's finally out there, and we're extremely excited. And JWST, right off the bat, found the furthest galaxies we've ever seen, way back in the early universe. Now, I wanted to sort of just talk about one more concept, just to contextualize my research, and this is the concept of redshifts and time. So here's a map of the universe starting at the Big Bang on the right and the present day on the left. And you can see time on the bottom, it's 0 to 13.8 billion years. And we have another unit called redshift on top. So we'll click forward. So the universe expands. And as it expands, it stretches light. This is called redshifting. And it means that if the universe is always expanding, we can use how much light has been stretched to figure out when that light came from. So a redshift of 0 is something that happened today, and a redshift of infinity is something that happened at the Big Bang. And instead of using gigayears or millions of years, we usually use redshift to identify how long ago an object existed in the universe. So the furthest away object we've ever discovered is at redshift 13.3, which is about 200 million years after the Big Bang. So if I use redshift versus age, this is kind of a graph to sort of guide you. So this is a recent paper by a group looking at galaxies. Okay. Now, the next 2 billion years, so giga means billion, is an exciting time for the formation of galaxies. So we form stars, and we actually form some small galaxies, but how do we get a big galaxy like the Milky Way? Well, the only way that we can get a galaxy as large as the Milky Way, which by the way is a pretty large galaxy, is by galaxies colliding into each other. So this is a period where lots of stars are forming and lots of galaxies are running into each other. And it's an exciting time for an astrophysicist. It's a hard time for a simulator. But this is where I focus a lot of my research. I love looking at galaxies collide with each other. And this is a wonderful time because we can see everything about this era of the universe, which means that if I'm a theorist and I want to make up a crazy theory, well, now I have actual observers out there telling me, no, that's wrong, you have to do that again. But it means that we can actually do science. We're not just in the realm of theory anymore, we can actually check our assumptions. Okay. Now, that's the intro of the universe. Any questions so far? And feel free to ask any question at all. I'm happy to answer any questions. Yes?
What do your simulations tell you about the Dark Ages?
They only tell me that it collapses in the cosmic web, not much else. In fact, what I did the last time I ran a simulation is I deleted the Dark Age time because I'm not studying it.
How about during reionization?
Everything. All of my research is basically in reionization. I'm going to tell you a lot about that going forward. Okay, radiative transfer modeling. What is radiative transfer?
We have one person with a question here. Sorry about that. Can you all please to them, please? Thanks for your offer.
What's a black hole?
A black hole is something that is so heavy that light can never escape it. So if you have a big ball of something, how old are you, by the way? 6. Okay. All right. So I would say that a black hole is a very dark object that's very heavy that you don't want to get near to. I'll also say that when a star dies, when a big star dies, it can leave behind a black hole. And I'll also say, as you go from 6 to 16 to 26, you'll learn a lot more about black holes. Okay, radiative transfer modeling. What does radiative transfer mean? And radiative transfer is the core of my research, so I have to define this word. It means the interaction between light and matter. All right, so I need to model how light and matter interact with each other. All right, so I made a simple, so there's pretty pictures, but I made this really ugly picture to sort of simplify the way I see the universe. So this is how I see the universe. 2 triangles. On the side of cosmological simulations, you have the beginning of the universe on the left side and the present day on the right side. And the width of the triangle tells you how much I trust that way of looking at the universe. So that means that I trust simulations right at the beginning where we have data from the CMB that we talked about. And as we propagate it forward, as we run these simulations forward in time, every misassumption that we make, every thing we don't have a theory for adds up. Even the computational error adds up. And we lose our ability to properly calculate what the universe might look like. So as we go towards the present day, we can make a simulation go to the present day, but we still have to work on making that simulation accurate. And then on the other side, we have telescopes. So if we take a telescope in space and we turn it back at the Earth, it can see a lot of things very well. And we have plenty of spy satellites that do that. We actually turned one of them into an observing telescope and turned it the other way. And it's a very good one, and it kind of shows us how good our spy satellites are. But as the telescopes look further into the universe, there's less light for them to see because the objects are far away and dim. And that means that they lose their ability to properly characterize and understand our universe. And so what I do is I work in the region where these two things overlap, where we have enough faith in our telescope data and we have enough faith in our simulations that we can think about how the two of these the theory and the observations affect each other. And I try to improve both sides. So on the simulation side, I have two types of simulations. I call them both kitchen sink simulations because I like putting everything in my simulations. You can take stuff out and it can run much faster, but I'm really interested in the details. So I put every bit of physics in the simulations and makes them run very slow and take a lot of computers, but I like that stuff. So there's one of them where I zoom into a single galaxy, and there's one of them where I make a lot of galaxies. That's the zoom in and the large box simulations. And then I'm interested in lots of different telescopes as well. I use ENSO. One more slide. There we go. So I like the Hubble Space Telescope, the Keck telescope that's on Earth, and the James Webb Space Telescope. And then I'm looking forward to lots of wonderful big telescopes that are coming in the second half of this decade. So this is sort of the ingredients for what I like to work with. And the problem with wanting to improve and use both types of ways of looking at the universe is that you need a common language to be able to talk between telescopes and theory. Basically, for a long time, these two things didn't really overlap. And that meant that theorists would do whatever they wanted to do, observers would do whatever they wanted to do, and the two communities wouldn't really have anything to say to each other. But now is not that time. Now with these two areas overlap, so now we need a common language. That language is what we call synthetic observations. So what I do is I take a simulation, and I trace light from every single star in the simulation all through the galaxies and through the space between galaxies all the way back to a telescope to make an image of what a telescope would see so that I can compare telescope images right back to what the theory says. Okay, so I make all these things. So there's a list of things over there. One of them is photometry. So to define photometry, these are just pictures. So this is JVST on the right, and then Hubble on the left. And these are just pretty pictures of galaxies. And the goal of my simulations is to be able to make those pretty pictures out of my simulations. I can tell you that has taken me 10 years to figure out. It's a lot of work, but it's been paying some dividends. All right, and then the second thing that was on the list, or the second and third thing, are spectra and nebula emission. So I'll try to explain this quickly. So if you have a star, it has different brightnesses and different wavelengths of light. And if that light hits a cloud of gas, the gas will absorb the light, and then it'll re-emit it in different wavelengths. So in the middle, you'll see spikes in different wavelengths, and that's light coming from the gas. And if you look at the star through the gas, you'll see less light, so it'll have the opposite. It's called absorption. So it'll be absorbed or emitted based on how it interacts with the gas cloud. So part of radiative transfer, part of what I do is I trace the light through the gas, it'll interact with the gas, and it'll come off and then change the light. So this is an example of what I can do with my simulations, and this is what they look like when I do radiative transfer. Can you go forward one bit? So what you'll notice, one thing about this is that it's moving. So on the left, we have a protogalaxy, a very small galaxy, and it's trying to find its shape. It's trying to turn itself into a spiral galaxy. And what I've done is I've looked at all the wavelengths of light and all of the chemistry, and I've produced what that galaxy might look like through a telescope if you're able to get the best telescope that we have. And I also look at, so in this top center, it's all of the wavelengths of light, and you can see these spikes going up, and that has to do with chemistry. And then we can go to the next slide. There's some details here that don't really matter, so we can go straight to the next slide. There's a bunch of words. But this allows us to start investigating a few things from a few different angles. So let me start with the theory side. So one bit forward. So the universe started with just hydrogen and helium. These are the most basic elements in the periodic table. And The only way that you can make heavier things like carbon and oxygen, and like I keep talking about, is through nuclear fusion in the center of a star. So our star is continuous, like our sun is always making helium out of hydrogen, bigger stars are making carbon out of helium, and all of the elements that are basically make up our body that aren't hydrogen and helium come from the center of a star. So the longer a galaxy forms stars, the more of these heavier elements it has. That's the theory. Now, the problem is, in the center of our Milky Way galaxy, there's stars that we know that have a lot of heavy elements that are very old. And this is wrong. They shouldn't have, the old stars shouldn't have heavy elements. And the question is, why is that so? So I created this simulation, and each dot is a star. So I got rid of all the nice things in the simulation. I just plotted the stars. And the color is how much metal it has. So it goes from a purple to a yellow. And these two galaxies are merging into each other. So I'm just looking at what happens to stars when two galaxies come together. And if you look closely and you keep watching, you'll see something start to change because they just made one pass. So they're going to rotate around each other and try to crash into each other. You can actually see in the top galaxy, and it's happening in the bottom galaxy too, the colors are changing. Right. So it's going to make a couple passes. It's going to take a second. But what this simulation showed me was that if you want to create something like the Milky Way, you're going to need to have two big galaxies a long time ago crash into each other just like this. And then it forms, in the end, an arrangement where there's lots and lots of metals in the center, even though these galaxies are very old. So what this taught me is that merging galaxies create metals. So this is looking face on the galaxy. So it's a spiral galaxy looking like this. Okay? So this is one of the results of my research. Now, the importance of time domain studies. So what does time domain mean? Time domain means things move in time. You've seen the last two slides had movies, which are pretty, and the galaxies moved. And I learned something from the movement of these galaxies. Now, why would I have a slide talking about the importance of it? Because when I was doing my PhD, I didn't have my own simulations. My advisor made simulations. I could only look at one point in time from these simulations. And I created images of those times, and I made predictions for JWST. These two on the right are from JWST. There's one from Hubble Space Telescope, like what this galaxy would look like through those telescopes. This is when I thought things would launch in 2018. But I could only look at one period in time. And I could do a lot of things with that, but I couldn't tell a story. And I might not need to convince this audience that it's important to look at things moving in time in order to understand them, but this was not the way things were done back in 2014. You only looked at one point in time. So I could look at lots of different chemistry and things like that, but I could only look at one point in time. So once I finally left my PhD and I started doing research after that, I could find enough supercomputers to run my own simulations. I started to look at things as they moved in time. And next slide. One more. Okay, so this is the galaxy that I had before, and a little bit forward, and a little bit forward. Okay. So what I learned when I started to do these, and this was new at the field at the time, so this is around 2018, is that galaxies, when you put them in motion, they do very, very interesting things. This galaxy isn't moving the way you think a galaxy might move, especially if you're thinking about creating a spiral galaxy. And it turns out that galaxies in the early universe are very messy. And when things are very messy, it means that all the models that people made about them that assume that things are not messy need to be rethought of. So this is one of the reasons why I really love to make simulations that move in time. Now there's a problem with that. You can see the time moving. It's saving the entire universe every 300,000 years for billions of years. That takes all of the memory, all of the storage space I could ever find. This is a problem. This turns into a problem of data. What to do with the data, how to store the data, And it turns out that I need more data space than I need computational power. But when I do that, I learn a lot of things about galaxies. You can continue forward. Okay. I found that if I save the galaxy once every million years, I can learn almost everything about everything that happens to a galaxy over time. So these are just graphs of pretty different things that happen to galaxies. The top left is how many stars versus the mass of the galaxies, metallicity in the bottom right. These are different variables that I've been looking at through galaxies. All right, next slide. So if you could go to the end of this slide. Okay. So on top of looking at galaxies over time, I did a lot of simulations. Keep going. And what I found is, and I'll try to explain this quickly, but what I found is that if I look at all the points in time and I look at a lot of simulations, everything starts to overlap. And when you do that, if you have enough data, like if I just ran 8 simulations and look at the end of the simulations, I'd have a little data. But if I've looked at all the time and all the simulations, I have a lot of data. And if I have a lot of data, I can start to characterize everything that could exist. So I don't have time to go into this particular plot too much, but what I found is that you can characterize every galaxy's light but with 2 different variables, and you can characterize its metallicity with those variables as well. So it turns out that if you do a few simulations but save it for a lot of periods of time, it is a lot more efficient than trying to run a lot of simulations. So here I have 8 simulations, and I fully characterize all of the galaxies in the early universe. All right, move forward. You can pass this slide. Okay, and you can actually keep going through slides. I'm going to go to some of the punchlines at the end. Keep going. Keep going. All right, JDST is the punchline. So we'll stop here. So JDST is an infrared telescope. So this means that it looks at wavelengths of light that are longer than red. So you can't see any of these galaxies that JDST sees with the naked eye. But what it allows it to do is it allows it to see galaxies that are further away than we've ever seen before. Now, there's a problem with looking at really far away galaxies, and the problem is that if you look at something that's very far away, it's just one point of light. It takes a lot of effort to get just any of the light from it, and you end up with just a galaxy that's defined by 3 or 4 numbers in the end. And from those 3 or 4 numbers, you're trying to understand as much as you can about this galaxy. And the only way to take 4 numbers and try to learn something about a galaxy is to have a detailed understanding of all the possible galaxies, and then a very precisely made algorithm that figures out what you can from this. So the whole community has been trying to figure out algorithms as well as my group. And what I do is that I take those 4 wavelengths of light. So there's buckets of light. These are the things in the top middle. These buckets of light, they take in light, and you get numbers from each one of these buckets. And I try to figure out, first, what the redshift of the galaxy is. And the redshift tells me how long ago the galaxy existed and how far away it is. And I'm here to tell you that we haven't had, like the broader community hasn't had a lot of success in trying to figure that out. There's galaxies that in the first data releases could either have been from 13 billion years ago or 5 billion years ago, either one. So can you go to the next slide? So this is for a particular galaxy that was part of a work that was published, and I was part of this group in 2023. This is this year. And what you see on the left is a bunch of probability curves of what redshift this is, reminding you that redshift is a proxy for time. So there's a broad range from 10 to 12 for some of them. These are all the different estimation techniques in the field. Now, our estimation technique is the one that goes vertically upward. So what we did is we took all of our simulated galaxies and we used machine learning to figure out how to more precisely figure out how far away galaxies are. So this is one of our results of our research. And this was a work that I did with my graduate student, Lillian. And the next one. And then another thing I was pretty excited about is figuring out the history of a galaxy from those 4 points of light. So on the top you have, there's 4 dots that really hard to see in there. There's 4 dots which represent those 4 points of light. And from those 4 points of light, I figured out the age of all the stars inside of this galaxy. I found out that they're about 70 million years old. There was a burst of star formation. And this is a galaxy that's very far away. So this is an actual galaxy in the sky. And the goal of this project is to figure out and find the oldest star that we could ever observe in the universe, to figure out what happened to the first stars in the universe. And by using all of my simulations and all of the modeling that I've done, we're able to characterize the real galaxies with JWST and figure out as much as we can from just a few points of light. Okay, so in the interest of time, I'll do my summary, and I'll take any questions. Thank you very much.
All right.
Yeah.
Did you want to? I'm sorry. Did you?
No.
Oh,
Yeah.
sorry about that.
I'm not going to read my summary, so you can read it if you like.
They can all read it up there. Okay. Well, yeah. Thank you so much, Professor Barrow. Does anybody have any questions for him after this? Yes, I'll bring it over.
Yes, when you're talking about 4 points of light, what does that refer to?
4 different wavelengths of light. So it'll be something that is in the mid-infrared and the far infrared and so forth. So it'll just be 4 numbers. It'll be, yeah.
So does every galaxy have a black hole at its center?
I haven't been to every galaxy, but we think so.
So you've seen black holes in all the galaxies in our local group?
So black holes are, well, technically you can't see them. So we have the Event Horizon Telescope, which had a famous result in the last few years, where it looked at and was able to record a light that was trapped around a black hole, around our own central black hole in the middle of the Milky Way, and one that's a little further away in the Virgo cluster. In order to, you can see jets coming from black holes if the black holes are sucking in material. You can see, in some black holes that are nearby, you can see stars orbiting them very quickly, or the gas orbiting them. You can see quasars, which are black holes in the early universe, are very bright, and we can figure out how big those black holes are. But we've seen evidence that every galaxy that we have the ability to look into and see a black hole that's around a certain mass range and bigger, we see a black hole.
The simulation that you showed of the early galaxy and its messy behavior, it looked like it was doing something similar to vortex shedding in liquids. Do hydrodynamical principles hold on those larger scales with stars and not just the gases that make up the galaxies?
So to answer your question about if hydrodynamical principles apply, yes. What was happening most of all was that there were supernovae that were disrupting the gas and causing these explosions inside of the gas.
Any other questions for Professor Barrow? Oh, I'll be right over there. Yep. Thanks.
Yeah, thank you. First of all, thank you for giving such a great lecture. It was really fascinating. And just out of curiosity, you said that these simulations do take a while to run. So how long do they
How long do they run?
Yeah, just out of curiosity.
So I recently got an allocation for 1.5 million core hours. So that means one processor running for 1.5 million hours, and I expect to run 3 simulations of this. So I run it on a lot of cores. So in human time, it takes about 6 months to run a simulation.
That's insane. Thank you so much.
Did you want a question? No. Yeah.
Do you use the supercomputer at the U of I for that?
So traditionally, I've used the Texas Advanced Computing Center's Stampede supercomputer, but they closed down in the summer. And since I'm a professor at U of I, I've switched to the Delta supercomputer at NCSA. So yes, I do. And I'm supporting my own local supercomputer.
Any other questions, folks? All right. Well, let's thank Professor Barrow for coming here to give this great talk. Oh, did you have another question? I'm so sorry. I didn't see your hand up. My apologies. If you don't. You all okay with clapping again, right? Can you get that? Thank you.
What's the most scientifically accurate movie as far as galaxies and stars are concerned, and what is your favorite one?
It's not a movie, but I've been watching For All Mankind, and I find it nostalgic and fairly accurate. I like hard sci-fi a lot.
Thank you.
I've had a lot of fun with watching that show as well. Thank you for sharing. I appreciate it. All right. Well, again, yeah, thank you so much for joining us this evening, Dr. Barrow. Anyways, if you folks are sticking around for our other shows this evening, we are playing Season of Light throughout the month of December. If you do have tickets for that show, I would ask that you step outside. I'm going to get those doors open over there. By that, I mean I'm going to get our staff member to open those doors. And then we also have our Pink Floyd show with the Dark Side of the Moon playing at 9 o'clock. For our next Kaler Science Lecture, we have invited a professor from the U of I's Department of Chemistry, Martin Burke. The title of his talk is called Imagine a World Where Everyone Can Make Molecules. So you can, I guess, chew on that for a few months, because that talk will happen on February 2nd. We'll actually have to have 2 talks in February next year, because we won't have a talk on the first Friday in March, because we'll actually have a theater production here in the planetarium that weekend. All right? So thank you all so much again for joining us this evening at the planetarium. We hope to see you again soon. All right?